So we are going to continue our discussion about SVM. And so a quick recap, what we have discussed so far is basically we have derived these three equations, which will help us in finding the equation of the hyperplane or this linear hyperplane over here. Okay, these are three equations. Yeah. And then the following example is just apply what we have derived using a concrete data set, in a sense that our data set over here is the x is 1, 2, 2, 1, 4, 4, 5, 5. Then the so-called label, okay, the feature, I use the feature. Okay, the feature is 1, 2, 2, 1, 4, 4, 5, 5, and the label is a -1, -1, +1, +1. Okay, and then we solve this very simple problem using this basically to fully understand the inner workings of how to apply what we have derived in the previous slides. Okay, not only one slide, multiple slides. We have we end up we have gotten this particular these three equations. All right, yeah, then we can solve it and we can get the width value. And then once we know the width, we know the basically the width and this is actually just a linear line. So you can also see this is the width, this is the bias, no problem. All right, so far what we have discussed is all about the problem that is linearly separable. Right, so 2 points here, 2 points there, and we can draw a linear line to separate these two classes. Yeah, so what if the problem is not linearly separable? For instance, okay, so this is just in one dimensional, just like a number line, okay, 1D. And then we have these 4 points. Okay, so in a sense that our feature value over here is so you see this one, so this is these are 4 values, 0, 1, 2, 3, and the label they are positive, negative, negative, positive. Okay, if we introduce the 1, we use a positive 1 to represent positive sample, negative 1 to represent negative sample. Okay, so this is our data set. We are going to build a model later. And you look at this data set. This is one dimensional because we only have one feature. And this is like in a number. This is like in a number line. How do we draw a linear line to separate these two classes? Yeah, think about it. Can we draw a line here? Yeah, you can, but you have one sample that is wrongly classified, wrongly yeah, by right this positive, this positive, this should belong to the same class. And now you basically are trying to say, oh, on the left hand side this is one class, and on the right side of this linear line this is one class. But this is not the case because clearly we see that we got one sample that was wrongly classified, right? Then how about let's try the other combinations. I mean the other possible solution. Okay, I cannot erase anyways. Okay, so what if we draw a line over here? Let's say we see, yeah, this linear line, we draw a line over here. Again, we got the one sample that's wrongly classified, right? This sample. So by drawing this line, basically you are trying to see, okay, on the left hand side of this linear, this line, we have one class, and on the right hand side of this linear line, we have another class. But clearly, the positive class, they were not so-called like grouped together, right? Yeah, then any other possible solution? Let's say we draw a line over here. Then both are wrong. Okay, on your left, you have a mix of positive and negative. On the right, you also have a mix of positive and negative. It's like you split your decision tree. Yeah, we want to pursue the pure node, right? The node with only one, only samples belonging to one class. Okay, but clearly over here on the left we got two classes. On the right we also got two classes. Yeah, so this is actually the worst. Okay, so which means although this problem looks pretty simple, just 4 samples and one, in a one-dimensional space, yeah, 1D, one feature, and this column for the label. But this problem cannot be solved using what we have derived from the previous slides. Okay, directly applied. Okay, using the formula, I mean the equation we have derived. Yeah, so in the sense that this problem is not linearly separable. Yeah, so this is where the very powerful idea kernel comes into play. Kernel is basically just a function. Okay, kernel is not like the kernel in your Jupyter notebook. Okay, not that kernel. It's actually just a function. We just use a fancy name, kernel function. Okay, the purpose of this kernel is to transform an input data space into the required form. In other words, you just apply the function. Okay, so these are the keywords already in the red this red color font. The kernel takes a low-dimensional input space and transform it into a higher dimensional space. Okay, and let me finish this. I'll give you an example. We can see that it converts a non-separable problem or inseparable problem to a separable problems. Okay, problems to yeah, and by adding more dimensions to it, it is most useful in non-linear separation problem. For example, this is again the same data set we have seen from the previous slides. This is a simple feature label table, and in 1D, one-dimensional space. And then clearly for this case, we cannot draw a draw a line to separate these two classes. Yeah. So what if we somehow increase the dimensions? Okay, from 1D, this is a one-dimensional. Yeah, we increase the dimension to two-dimensional, 2D. All right, if we make some function that we try to transform our original values, original numbers into a higher dimensional, and clearly we look at this the second plot. Okay, this is linearly separable because I can see I can draw a line over here. Where's my okay? I can draw a line over here. Yeah, this become our conventional SVM problem that we have two classes, on one side. I mean, this one class on one side and the other class on the other side. Okay, so basically the idea is whatever problem we cannot solve at the lower dimension, let's try to increase the dimension, and hopefully in a higher dimension the problem can be solved. That's why the keyword is we are going to take the lower dimensional input and transform into a higher dimensional space. And hopefully in this higher dimensional space, the problem can be easily solved by using our derived SVM equations. Okay. So we have understood that the optimization of basically the solution for SVM depends only on the dot product of pairs of support vectors, right? Yeah. Then, however, as our very simple example just now demonstrated, with all these support vectors in its original form, I mean, for example, in its one-dimensional space, it is not linearly separable. That's why we need to transform them. Try to increase the dimensionalities. How to do that? We use this symbol, this phi, to denote the transformed xi. Xi is a support vector. Okay, xi is a support vector. Yeah. So now instead of computing this xi dot xj, like what we did in our original, using the original data, original feature values, support vector values, we compute this transformed xi multiply with a transformed xj. Okay, so this transform just for simplicity, just understand it as a higher dimensional support vector. Okay, we are going to use a function to transform it. Yeah. So and it can be expressed as a kernel function, this k. So just because you can clearly see this dot product is also only dependent on this xi and xj. So in a sense, the xi and j are the so-called independent variable, and we use the k to denote this kernel function. And arguments that are required are this xi and xj as well. Okay. So now the question is, how do we come from this original xi, for example, this is our original form, our original one, and to this transformed xi transform. Yeah, this is very, yeah, basically how do we increase the dimensionality so that we can solve the problem. This kernel function is called a polynomial kernel. Yeah, it's basically all about polynomial, right? So then we use this kxi xj is equal to this gamma xi dot xj. Yeah, or and here is a dot product. It literally means that the xi vector is going to multiply with xj vector and plus another term r and to the power of d. So what are they? Yeah, d is the degree of the polynomial kernel function, gamma is the kernel coefficient, and r is the independent constant term. Yeah. Okay, enough math. Let's look at one concrete example. Yeah. Yeah, let's use this example to understand how polynomial kernel works. Yeah, since this is a one-dimensional, yeah, we can finally get rid of this arrow on top of the x, okay? Because one-dimensional is just a scalar, right? Yeah. So basically, a scalar set, by definition, is just a one-dimensional vector. Yeah, that's why we can finally get rid of this arrow on top of this x. Yeah. Then let's give some numbers for this polynomial kernel function. Let's define gamma is 1. Okay. Gamma is 1. R is 2. D is 2. Yeah. Then this polynomial kernel function has been simplified like this. Your gamma is 1, so 1 over here. R is 2 plus 2. D is 2, so to the power of 2 squared. Yeah. Then this xi vector dot xj vector, since now they are just a scalar. I mean, in this one-dimensional number line, it's just a scalar, so we can just use xi multiply with xj. Yeah, no need to consider vector anymore on this one-dimensional space. Plus 2 squared. Okay, then we expand this one. This will be equal to vector dot product. Okay, so if you look at this one, to verify, it's you can see 2xi, 2xj, so it's basically 4. It's basically 2xi multiplied with 2xj plus, yeah, this xi squared plus multiply with xj squared plus 2 multiply with 2. Okay, we got 4xi xj plus xi squared xj squared plus 4. Right? It's just like how we multiply, how we do the dot product for these simple vectors. Let's say we have a vector of 1, 2, and 2, 1. Okay, these two vectors. How to do it? Just 1. Okay, maybe change the number. 1, 3. Okay, so just this 1 multiplied with 3 plus 2 multiplied with 1. Right? The same thing. So we got over here we got 5. Okay. So it's basically if you are familiar with this kind of vector dot product, clearly you can see over here it's actually multiplication or dot product of two vectors, and now we just split them. 2xi and xi. The first basically the value in the first coordinate, I mean in the first dimension is 2xi, in the second dimension is xi squared, in the third dimension is 2, right? Okay. So these are just the transformed xi and xj, xi vector and xj vector. Okay, you can see our xi, xj was in this one-dimensional. Now basically we have so-called transformed this xi and xj into three-dimensional space, right? And now we can let's use numbers. Let's use the numbers. You see our for the first sample, okay, this is I is the sample index. Okay, so for the first sample, so in a sense, this is the first sample, this is the second sample. So negative first. Yeah, let's get negative down first. And then this is the third sample, this is the fourth sample. Fourth sample. Okay. For our first sample, the original value is 1. And we doing it after we do this transformation, you see 1 over here, you use this transformation. 2 multiplied with 1 is 2. 1 squared is 1. And the last one is a constant. right? And then for the second sample, this is a 2, and after transformation by using this by using what we have derived over here, this is 2 multiplied with 2 is 4. 2 squared is also 4, and the last the last value is just a constant 2. And similarly for this positive sample, this is 0. So 0 multiplied with 2 is 0. 0 squared is also 0. And the last coordinate is just 2, the constant 2. And this 3 multiplied with 2 is 6. 3 squared is 9. And the last one is 2 as well. Okay, now can you see that we have successfully transformed our original numbers, these are samples in one-dimensional space in this on this number line to coordinates with 3 dimensions. Okay, so in a sense that the coordinate for the first point is 2, 1, 2, for the second point is 4, 4, 2, for the third point is 0, 0, 2, for the fourth point is 6, 9, 2. The linear, this kind of polynomial kernel function. Okay, now let's try to visualize the process. Okay, yeah. So this is our original data set. Yeah, original data set, we have these are 4 samples, x1, x2, x3, x4, and the corresponding, the feature value are 0, 1, 2, 3, and the corresponding labels are negative, negative, positive, positive over here. And after we have done the transformation, and we got into 3D, okay, right? These are from 1 to become 2, 1, 2, and 2 become 4, 4, 2, 0 becomes 0, 0, 2, 4, 3 becomes 6, 9, 2. Since the last, the last the coordinate, the third coordinate is the same for all the basically for all the points. We can ignore the last coordinates. Okay, we can just plot this 2, 1 over here, 4, 4 here, and 0, 0 here, and 6, 9 over here. Yeah, if you really want to introduce the last coordinate, you can do so. You just introduce another dimension, and all these points will just coming to you by 2 steps. So can you observe that it now becomes linearly separable in the higher dimensional space? Yeah, so previously we cannot draw a line to separate these 2 so-called classes. Now roughly I can observe, okay, my hyperplane should be somewhere over here, or maybe over here. Yeah, or maybe over here. I don't know yet, but clearly I know this can be separated based on my observation. But which line to choose? Let's come back to our original problem, right? Our starting point of this SVM. So which line is optimal? Which hyperplane or which decision boundary is the optimal one we are going to choose, right? So yeah, we come back to the same problem. Then let's see. So back to this expression. We have just basically copy the same thing from here, no difference at all. And the final 2 expression, these are just the transformed xi, basically the support vector. This is also the transformed support vector, the same thing. And you can see the final results is just the dot product of the transformed vectors, right? And then the amazing thing is that we actually do not need to transform each individual support vectors and calculate their dot products. So it's like since our final goal is to calculate this transformed xi dot transformed xj. Okay, maybe you have already forgotten. Let's go back to where we started. So originally, all the calculation was based on the dot product of the xi and xj in the original form, and we noticed that this cannot help us to solve the problem, cannot draw the decision boundary, and we are going to calculate the transformed xi dot transformed xj. Okay, we want to get this, and so we notice that by using this kernel function, we can get this so-called transform xi dot transform xj. And then over here, yeah, so our final goal is to get this transform xi dot transform xj. And then look at this one. What we need to do is just to plug in the original support vectors into this expression. blue square, in this blue rectangle. Okay, because this one essentially is equal to the final transformed transform xi dot transform xj. Yeah, since this effectively equals, they're not equivalent, they're not approximately equal, just exactly equal to this transform xi dot transform xj. So now our problem become very simple. We do not need to go through this kind of this kind of expansion, then simplification, then kind of like to basically all of those intermediate mathematics. We can skip all this. It's a huge improvement. What we can do is just plug in our original xi, original xj, basically the support vector values, and find their dot product plus 2 squared it. That's about it. Okay, because this finally is equal to this transform xi dot transform xj. All right. Any questions about this? Take a look. 5 seconds. Then during our calculations, we can actually ignore all this. We don't need to spend time on this because clearly we know this equation or this expression will give us exactly what we want. That is phi xi dot phi xj. All right. Okay. Let's continue. So let's apply the polynomial kernel to solve this problem directly. So this is our original derived equations. Yeah, you can see it was all based on the dot product of support vectors xi and u. Again, u is just a free variable, and if u somehow pointing to the positive support vector, we need to follow this equation. And if u somehow pointing to the negative support vector, we need to follow this equation. So now we know that our original dot product cannot help us to solve this problem, this linearly inseparable or non-separable problem. We are going to have this introduce this kernel function kxi comma u. Basically apply our kernel function over here. And then so you can see the change is only in this dashed blue rectangle. And so this is also the same condition when u is a positive pointing to a positive support vector, and the second equation is when u pointing to the negative support vector. And also do not forget our this very important derived equation. Let this beta I is equal to alpha I yi, same as what we have done previously. And so now these are our three equations that we have. So instead of the original xi dot xu, we are going to use the transformed xi dot transformed xu. Transform the u. Okay, u is if u pointing to the support vector. All right. Then you can see we just plug in the numbers. Plug in the our support vectors, and over here you can see the first equation is when u pointing to x1, this x1 support vector. Okay, the second, then you can see we plug in all these numbers, x1 over here, x1 over here, x1 over here, x1 over here. Okay, then this I got iterated from like this one b1. So basically this one will be because this one is beta 1. We use beta I to represent alpha I yi. Yeah, so beta 1, beta 2, beta 3, beta 4, and plus b is equal to -1. Why -1? Because x1 is a negative sample, so it's a -1. Then let's look at one more. Maybe this the last one, x4. This is when the last equation is when u is equal to not the last, second last equation is when u is equal to x4. And x4 is a positive sample, so we're going to use the first equation and just substitute this u with x4. So x4 over here, you can see x4 over here, x4 over here, x4 over here, x4 over here. Yeah, you'll notice that the only change along the writing of these four equations is only about over here. The rest of things are the same. On the left hand side are the same. Only this got changed. On the right hand side, you need to change the sign of this sample accordingly. Okay, the rest of things are basically the same. That's why you see a lot of repetitions. Okay, and also the very important condition is alpha I yi, and we add them up is equal to 0. So you just beta 1 plus beta 2 plus beta 3 plus beta 4 is equal to 0. All right, then over here you can see 5 equations. Yeah, 5 unknowns, right? Beta 1 all the way to beta 4 and plus and also this b bar. These are 5 unknowns and 5 equations. Yeah, based on what Dr. Side already covered, 5 equations, 5 unknowns. If the determinant is not equal to 0, you are going to have one unique solution. If the determinant is equal to 0, how many solutions do you have? Yeah, many solutions, right? Many solutions. Okay. Then yeah, we have this kernel function, polynomial kernel function, and we set this gamma as equal to 1, r is equal to 2, and d is equal to 2. And basically this kernel function has been simplified like this. Then we see how to calculate the k x1 x1, k x1 comma x1. You know, just apply the formula. Apply this function, this polynomial kernel function. What is x1? X1 is 1. Okay, so over here is basically k x1 comma x1 is equal to follow this equation. I mean follow this what you call it? Follow this function is x1 dot x1 plus 2 squared. Since this is in the so-called one-dimensional space, vector just a scalar, so we can get rid of this arrow on top of each of these x. So it's going to be just x1 dot x1 plus 2 squared. X1 is what? X1 is 1. So it's 1 here dot 1 plus 2 squared is equal to 9. So this is the so-called transformed dot product between this x1 and x1. Okay, transform dot product. Then let's take a look at take one more. Maybe this k x2 x1. Let me write down over here. So k x2 x1 follow this formula. This function is basically x2 dot x1 plus 2 squared. What is x2? X2 is 2. So then this will be 2 dot what is x1? X1 is 1 plus 2 squared. This is 4 squared is 16. So yeah, over basically means this number is 9, this number is 16. So at end of the day, these are still just numbers, nothing else, just numbers, right? Just yeah, and also whole numbers. We like whole numbers, right? Maybe try one more. Let's see. k x3 x4 x3. K x4 comma x3. Yeah. So this is like just like a comma. This is just like when you write your function in Python, you define a function. Then over here you have your first argument as A, second argument as B, third argument as C. So in case you have forgot this kind of notation over here. So whatever in the parentheses, these are just the input arguments. All right. If your math is not very strong, you try to understand from programming point of view. Okay. So then let me get rid of this. Give me some space. So this is equal to apply this formula again. So it's equal to x4. X4 is what? X4 x3 plus 2 squared. X4 is a 3. X3 is a 0. Oh, this is nice. 0 plus 2 squared. So this is equal to 4. Okay. 25? 3 times 0, right? 3 times 0. 3 times 0 is 0. And plus 2 is 0 plus 2 is equal to 2. 2 squared is 4. Okay. Alright. So this is how we calculate this one. So at the end of the day, the SVM problem still have been converted to this kind of a system of linear equations. All right, so yeah, we plug in all the numbers, like say 9, 16, 4 over here, like 9, 16, and 4 over here. We can calculate. You can double verify all these numbers. I believe all correct. And then 5 equations, 5 unknowns. And because we have, and this case is the case of many solutions. Okay, we got one free variable. If you solve this one, and we define beta 3 as the free variable, and these are just all these expressions. So beta 1 is equal to 2.375 minus 3 beta 3. Beta 2 is negative 4 plus 3 beta 3, and so on and so forth. Okay. Yeah, so beta 3 is a free variable. So basically, beta 3 can be anything, right? Of course, you can set the other. For example, I use the beta 1 as a free variable, and I express the other, beta 2, beta 3 as a expression of beta 1. Also no problem. Okay, so over here, I just use the beta 3 as the free variable, and so it can be anything, right? Let's choose the beta 3 as the simplest one. Beta 3 as 1. Okay, the simplest one as 1. And uh, then, okay, over here, so beta 1 is equal to negative 0.625, beta 2 is negative 1, beta 3 is 1, beta 4 is 0.625, and b is 1. So this is one set of solution we are going to use. Okay. The rest of the solution are going to be you know um similar to this, yeah, except they will be skewed. Okay. If your beta 3 value is not 1. Okay. So then remember our hyperplane was remember it was w dot u plus b is equal to 0, right? This is our hyperplane was this equation. Okay, and then our w originally was based on what we derived is alpha I, yi, and xi vector, the support vector. Okay, yeah. So then our this expression we used to represent, basically to substitute this w into the original equation will be alpha I yi xi vector dot u plus b. Okay, meaning to say, yeah, maybe you have already forgotten this one. Let's go back and take a look. So in our over here, yeah, w is equal to alpha I yi xi vector, and this is a w dot u plus b. Okay, and yeah, so this is the expression for the hyperplane. Okay, for the hyperplane. So basically, uh, w dot u plus b equal to 0. All right. Then you can clearly see the final result of this hyperplane also only depends, not only depends on this dot product of this xi and u, right? Yeah. Then alpha I yi is beta I. We can calculate. Yeah. So only also depends on this guy. The same as our the two equations we apply to solve the problem. Yeah. I mean these two equations we apply to solve these three equations actually we solve the problem. And then that's why over here we can no longer use this where are you? We can no longer use this alpha I sorry, this xi dot xu. We need to use the transformed xi dot transform u. It's all about vectors dot product. That's why it's called support vectors machines. So that's why we change this one from xi dot u to become k xi comma u transformed dot product plus b is equal to 0. And then this alpha I yi is our beta value, our beta I value. Okay, then we have this beta I. So sorry, just to iterate this I value. So beta 1, yeah, kx1 u plus beta 2 x2u, beta 3 x3u, and beta 4 x4u plus b is equal to 0. Yeah. And we have calculated this beta 1, beta 2, beta 3, beta 4, and b value. And we also know these support vectors values, right? Yeah, and also the kernel function will apply. You also know this key function. We know the key function. Yeah, so hyperplane is essentially made of those u vectors that satisfy this equation or this equality. Okay, so since this one-dimensional, we get rid of this u. So we have this 0. So plug in the numbers now. Beta 1 is a negative 0.625, and k this one about this remember our kernel function. Our kernel function was k x1 u is equal to x1 dot u. Let's say this is a vector plus 2 squared. This is our kernel function, right? We apply the word here, kernel function. Okay. And then plug in the numbers, and then beta 2 is a negative 1, and over here, for example, over here, why we got this u plus 2? x1 is 1, so it's a 1 dot u plus 2 squared. Yeah, since this is one-dimensional, we can get rid of, we can ignore these arrows, this arrow on top of this each symbol. Okay, so it's a basically 1 times u plus 2 is a squared, so it's a u plus 2 squared, right? Okay. Then this one, the second thing also the same. We have this x2 over here, so it's basically we apply this the same formula will be x2 over here, x2 over here. So this is a x2 is a 2, so 2u plus 2 squared. Okay, we got this 2u plus 2 squared. Then about the third the third one over here is basically 4 times beta 3 is where is it? Okay, beta 3 is 1. Let's see this one. So beta 3 is 1. So basically it's 1 multiplied with this key x3 u. What is x3? x3 is 0, right? So it's a 0 dot u plus 2 squared. So 0 times anything just give us 0, right? So it's just 4 over here. That's why for beta for this term is basically 1 multiplied with 4. We got 4, right? Then similarly for beta 4, you can try it. And our b value is 1. So our final solution, I mean the final result is this. The final result is this. And you look at this one. If we simplify this one, it's actually just a quadratic equation. The final result just this one can be simplified as u squared minus 3u plus 1 is equal to 0. And quadratic equation, you can apply the formula you have learned. Remember the formula? That's 2a minus b plus minus b squared minus 4ac. Remember this? If you cannot remember, forget about it. Okay, it's in your O-level syllabus. So then we can use a calculator to solve this simple equation. Final separating point in this 1D. Okay, 1D you cannot see we have a line, right? 1D is just all the points. Okay, so these are separating points. Or you can see, yeah. And then also let's try to visualize it. Where are the points? So basically, we are going to see that I cannot erase. Let me erase all the drawings. Delete. Okay. So basically on this 1D number line, okay, we are going to have one separating point over here and one separating point over here. Now you can see the negative class is over here. The positive class is outside of the two separating points. Okay, so better visualization will be given by sklearn. Yeah, so the blue region is this 0.382, and this separating point is 2.62 of 2.618, and the middle region, the blue region, is for the negative class, and the red region is for the positive class. All right. And a better visualization, I believe I also provided. So how to visualize this one? 2 points in a higher, basically these are 2 separating points in a higher dimension. Okay, so remember we did some transformation about our original data points, right? Yeah, so originally it's a 0, 1, 2, 3, and we changed to 3-dimensional. Yeah, 2, 1, 2, and what's the number? You can, yeah, okay. So now let's say in 2-dimensional, it's like these 2 points. You can try to imagine these 2 points will go to, all these things will go up. All these things will go up. Basically, we'll from the original 0, now you go to the first one is still 0, 0. Second one originally was 1. Now it's become 2, 1. Third one was 2, now become 4, 4. And fourth one is 3, now become 6, 9. And including this point, these 2 points, they will also go up in 2D. In 2D, we can see 2 points determine a line. It's a linear line. Then clearly our transformed one was not in 2D, right? It was in 3D. So in 3D, just you add another dimension. You let this one come to your, you let basically all the points coming to you by, by 2 steps. And then the linear line become a linear hyperplane. So this is the hyperplane to separate, in the sense that you have 2 points below the hyperplane, 2 points above hyperplane. So in other words, these are the positive data points. These are the negative data points. All right. So these are just our final solution. And if we quickly compare with what we can get from sklearn, you can see this dual coefficient, our beta value. We got the same thing, negative 0.625, negative 1, 1, 0.625. And the p value is 1. Okay. And this is the decision boundaries. I mean the decision boundary to separate these 2 classes. All right, 2 very important kernels. One is the so-called polynomial, the linear one that we have covered in our first half. Now let's look at the other one, the RBF kernel, radial basis function kernel. We are going to transform the original vector, support vector, into higher dimensions. And the miracle that is that the amazing thing is that we do not need to transform it one by one. What we want to do just to apply this this kind of function, okay? And then over here, gamma is the kernel coefficient, and uh, yeah, x, xi, xj are the support vectors. Yeah, look at this linearly inseparable problem. Look at this one. We have yeah, I even simplified his example, yeah, to make it more clear to see. We have x1, x2 over here, x3, x4 over here. Yeah, x1 is 1, 2, x2 is 5, 5, x3 is 2, 1, and x4 is 4, 4, and x1, x2 are the negative sample, always negative first. Let's get all this negativity, get rid of negativity first, and then we have these positive things, x3 and x4. Okay, and then look at this one. Can we draw a line? Can I draw a linear line to separate these two classes? Can I draw something like over here? Hold on. Hey, something like this. No, we got some point wrongly classified. Yeah, if I draw a line like this, also no, right? We draw a line like this, also no. Okay, so the decision boundary in the sense that is something clearly we can see. So these are 2 points over here, 2 positive points over here, 2 negative point over here. Maybe, yeah, I draw a curve, something like this. Then below this curve, this is one class. Above this curve, this is another class. Yeah, then yeah, there are so many curves to be drawn. So this one, I like this. Yeah, which shape? Okay, what was the function of this curve? Right? Its mathematics must be represented by a function. So yeah, that's what we are going to find out. Okay, so let's apply this RBF kernel to solve this problem directly. Again, you see for our original SVM for the linear separable case, it's just based on xi.u, xi.u, right? Not just change the same thing as what we have done for the previous polynomial kernel. And then for the hyperplane, it just this is basically represent the w dot u plus b is equal to 0. And now instead of calculating xi dot u, we use a key xiu. And and this is our hyperplane. And do not forget this very important thing we have derived with a lot of effort. And we got these two expressions over here. All right. So then we can apply these three equations, and also the same thing, like beta I is equal to alpha I yi, and then just the first equation is just when u is equal to x1. Okay, basically the same thing. So we are just going to change these four support vectors for these four equations, and change the corresponding -1 or +1 accordingly. Now let's calculate k. Maybe let's see. I use a kx x1 x3. Let's verify this. K x1 x3. Okay, and our key function, our kernel function, is e to the power of a gamma. This is L2 norm squared. Okay, L2 norm squared. It is basically just L2 norm squared without subscript. By convention is L2 norm, and we set gamma is equal to 0.2. Yeah. And then to calculate k x1 x3, these are vectors. Now it's in two-dimensional space. We cannot just ignore the arrows on top of this x. Okay, yeah, it's no longer a scalar, it's a vector. We need to be very careful when handling vectors. So e to the power of -2, right? -2. And then this is a double pipe. x1, where is x1? x1 is this guy. x1 is a 1, 2. So it's 1, 2 minus, where are you? x3, right? x3, where x3 is 2, 1. 2, 1. Then squared. Then find the L2 norm. L2 norm is so this is basically a vector difference subtraction. So it's 1 minus 2, 1 minus 2, -1, and 2 minus 1 is 1. Okay, so in a sense that within a double pipes, this is just a vector. So then e to the power of -0.2 square root -1 squared plus 1 squared. Then apply this square root. Sorry, this is squared over here. All right, that L2 norm just square root of -1 squared plus 1 squared. So we have got 0.2, and over here it is 2, right? 2. So it's e to the power of -0.4. Okay, we can get the same thing. Yeah, e to the power of 0.9. E to the power of -0.4. Anyway, the results are already here. I don't the 4 2 x2 4. All right, xk2. So let's see. K x2 x4. So e to the power -0.2, and then x2 is what? x2 is 5 5, right? 5 5. So 5 5. x4 is 4 4. 4 4. Yeah. So this thing we got this as e to the power of -0.2 1 1 over here, then squared. So e to the power of -0.2, the L2 norm will be square root of 2, right? Then it's squared. We will have the same thing, e to the power of -0.4. All right, so all this can be calculated. They are just taking the numbers and plug into whatever this RBF kernel function, and this gamma value is what we need to tune at when training the model. Over here, just randomly set 0.2. Okay. All right, so these are just after calculating all these numbers. We got, for example, k x1 3 is e to the power 0, e to the power of -0.4. 1 3 1 3 1 3. Where are you? 1 3 1 3 over here. So we verify. So e to the power 0, e to the power of -0.4. Okay. Mm. Yes. Yes, because e to the power something. This is a constant. E is a number. E is a 2.718, right? 2.71. The so-called Euler number. Euler number. I mean, the whole problem of SVM has again converted or simplified into solving a system of linear equations. Amazing, right? Amazing. The 5 equations, 5 unknowns usually will give us one unique solution. But based on the math you have learned, this may not always be the case. Yeah, may not always true, right? May not always be true. Yes. Then you can solve it. You plug in all these 5 equations into a solver. You can we can get this beta 1 as -3, beta 2 as -3, beta 3 as 3, beta 4 as 3, and b value as -0.1. Yeah. Then our hyperplane is in this form. Remember? Yeah, over here, our hyperplane has been changed, updated to this form. And then we just plug in the numbers. And we calculate beta 1 all the way to beta 4 and b value. We know our x1, x2, x3 value. And plug in the numbers. So beta 1 is -3, and kx1u. Beta 2 is -3, kx2u. Beta 3 is 3, x3u. Beta 4 is 3 minus 0.1 because b value is -0.1 equal to 0. And this one, because we see we can further simplify it. This divided by 3 on both sides. We can get 0.033 over here. The rest of things we can get rid of the so-called coefficients. Yeah, looks more more appealing. So in the simplest form, we can say the beta value is basically just a coefficient, right? So it's just -1, beta 2 is just -1 over here. Beta 3 is -1. Beta 3 is 1. You see 1 multiplied with this k x3u, and beta 4 is 1 over here, and b value is -0.033. All right. And then, so what does this mean? Essentially, this actually, okay, I prepared the slide. Let's go to the slide. So we represent this u vector as u1, u2 as well, basically with a 2 scalar to represent a vector in this 2-dimensional space. And u1 is the scalar or the magnitude in the horizontal axis, and u2 is the scalar or the magnitude in the vertical axis. And we calculate, basically we represent, not calculate, we represent this particular kx1u. Again, applying the formula we have, that is e to the power of -0.2, and then you have the 2 support vectors, the L2 norm and squared. So x1 is 1, 2, u is u1, u2, and we can get kx1u as this, and then similarly kx2u as this, because x2 is 5, 5, x3 is 2, 1, x4 is 4, 4. We can all represent this one, right? And then for this, we know this actually represents the hyperplane, because this was derived from our hyperplane. Okay, we substitute all the information we have either known or we have calculated into this hyperplane expression. Yeah. So essentially, the hyperplane is made of all those u vector, all those coordinates, which satisfy this particular equation. And now we just express this negative kx1u, negative kx2u, kx3u, kx4u by using this thing. This looks pretty long. But we can draw it, because anyway these are just a equation, right? Just an equation. I have the latex form of this equation over here. All right. And let's see, so this is the latex. I use x to represent u1, y to represent u2. Okay, this is latex because this so-called plot, where you were that smooth, right? That smooth can support latex, yeah, but cannot support those kind of Unicode, I believe. So then we just copy. Oops, what? Something wrong. Okay, so just pick up. Okay, so now this is our decision boundary, the hyperplane. Okay, the decision boundary, decision function. Remember our 4 points? What are our 4 points? Tell me. 1, 2, 2, 1, 4, 4, 5, 5, right? 1, 2, 1, 2, 2, 1, 4, 4, 5, 5. Okay, this is negative, right? Negative. So you can see now the positive samples are separated from the negative samples. In a sense, within this so-called the curve, enclosed by the curve, this region is the the positive class region, and outside of this curve is the negative region. Okay, and yeah, then we also verify using sklearn. Oh, you can see the kernel here got updated. So then you can see the dual coefficients, basically our beta value, we got the same, and the intercept, the b value also got the same value. And finally, we got this kind of this Patrick hat curve. All right.